But it turns out there are also states that can't be factored as a simple tensor product of two vectors. And there are some of multiple tensor products. So we call these states entangled. We can similarly consider the state of n qubits, which is defined as a vector in a tensor product of n d-dimensional complex spaces. And as in the case of n equals 2, the state psi can be product, meaning it can be factored as a tensor product of n vectors, or entangled, meaning there is no basis that psi is a tensor product of n vectors in it. Now, there are some natural questions we can ask, like how to determine if a state psi is entangled or product, or how to quantify the amount of entanglement that state psi has. So you can consider different computational and statistical models to study these questions. And turns out thinking about these problems has been very influential in quantum computing and quantum information, both conceptually and practically, with applications ranging from studying quantum many-body systems to quantum cryptography. So in this talk, we're going to look at these questions from the statistical perspective. And the way we'll formalize this is by using the property testing model, which is a general model for testing the properties of a set of objects, in our case, pure quantum states. And famous example of this in computer science is testing the properties of Boolean functions, like if a function is linear or not. And in this talk, we'll be interested in testing entanglement in this property testing model, which means devising an algorithm such that when given m identical copies of a quantum state psi, it performs a measurement on these states. And if the state psi has at most certain amount of entanglement, the algorithm accepts with probability at least 2/3. And if the state psi is far from all the states that have at most that specific amount of entanglement, then the algorithm rejects with probability at least 2/3. And our primary goal is to find the smallest number of copies m needed for this task. So this is called the copy or sample complexity. But we eventually also care about the time complexity of the algorithm that I'll get back to it later. So there are two big things in this model that we need to clarify. One is how to quantify the amount of entanglement in a quantum state. And also, what does it mean to be far from a set of entangled states? So let's first look at how we quantify many-body entanglement in our work, which is by using a class of quantum states called matrix product states. So let's say we have two qubits. As we saw, their state is a vector in a tensor product space with some complex coefficients aij. Now we're going to assume that these aij coefficients can be expressed as the trace of the product of complex matrices ai and bj. So we have D of the A matrices and D of the B matrices, and we impose an important constraint on these matrices by making them be R by R matrices. So for a fixed R, we call the family of states we get this way matrix product states with one dimension R, and we're going to denote them by MPS of R throughout the time. So an example is when the state is a product state, which is a tensor product like this. And in this case, these A and B matrices are just complex numbers, and the bond dimension is 1. Another example is the bell pair. And you can see that we need some 2 by 2 matrices like these to generate the 1/√2 coefficients. So the bond dimension is now 2. And more generally, turns out any quantum state is in a tensor product of 2 dimensional spaces can be written in the MPS form if we let the bond dimension to be as large as D. And this is attained by this simple example of the maximally entangled state on the slide. So as you see, the bond dimension is kind of telling us how much entanglement we have in the state. If R equals 1, then the state is product and there is no entanglement. And as R grows, we can write more and more entangled states in the MPS form. So this was all about describing the state of two qubits, but everything naturally extends also to the general N case. So now we have the coefficients we deal with are the trace of N matrices multiplied together. And these matrices don't necessarily commute with each other, so their order actually matters inside the trace. And this means we are implicitly assuming an ordering of the qubits. So we assume all these matrices have rank at most R, or they're R bar R matrices. And again, one can show that when R is sufficiently large, meaning exponential in the number of qubits, then any state has an MPS representation. But for smaller values of R, we are restricting the amount of entanglement present. So there is another, perhaps more intuitive characterization of MPS as well, which we heavily use in the future slides. And this characterization says that a state is MPS if and only if the rank or the number of non-zero eigenvalues of its reduced density matrices on the first L qubits is bounded by R. And this holds when L is anywhere between 1 to n. So keep this characterization in mind. We'll return to it later in the talk. Okay, so besides offering a way to quantify many-body entanglement, MPS includes interesting physically relevant quantum states. And for example, the ground state of a 1D gapped local Hamiltonian has short-range entanglement, as formally stated by the entanglement entropy area law. And it's shown to be well approximated by MPS of small bond dimension. Another example is quantum computations that generate limited entanglement, as in short-time dynamics of local Hamiltonians or low-depth quantum circuits in 1D and beyond. So one nice thing about such low rank or low bond dimension MPS is that they require substantially fewer parameters to describe than a generic quantum state. So a general quantum state involving n qubits needs d to the n parameters, which, for example, leads to exponentially large copy complexity if you want to learn the whole state. But in contrast, an MPS with bond dimension R only needs n times d times R squared many parameters to describe the entries of all of its matrices, this is linear in n the number of qubits. And because of this concise description, and also the simple structure MPS has, we can have efficient learning or simulation algorithms for states represented by MPS. Okay, so that was all about introducing matrix product states. Now let's go back to the property testing model we had. And to test entanglement, now our goal is to design an MPS tester, which with high probability correctly decides if a state is an MPS of bond dimension R, or if it is far from any state in MPS R. Now, the only remaining ingredient that I need to tell you about is how we measure the distance to MPS. So there are two natural ways to do this. One is by finding the maximum overlap between a state and MPS R. And the other is to find the minimum trace distance between psi, now thought of as a density matrix, and states in MPS R. And as you see, these two notions are actually related to each other, and I'll switch between them throughout the talk. But I'll also reserve delta for when the distance is measured using the trace distance. And of course, the number of copies M that the algorithm we have uses depends on this delta, and also the number of qubits and the bond dimension R. Okay, so this is the model. So as I mentioned, our goal is to find the optimal algorithm that requires the fewest number of copies. And ideally, we can ask if a constant number of copies, independent of the number of qubits in the state, is sufficient. So if you think about it, there are really two conflicting demands here. On one hand, any MPS tester should somehow check that the rank of each of the n cuts is less than R. And unless we reuse some of the copies when we are checking different cuts, this means we need a number of copies that grows with n, the number of qubits. So this suggests that to get a constant number of copies, we should reuse some of our copies and avoid bringing fresh copies for checking each cut. But then we also know that measurements in quantum mechanics are destructive. And the measurement we perform for checking one cut could potentially disturb the outcome of checking the rank or the bond dimension of the remaining cuts. So this suggests that we shouldn't reuse our copies. And in general, it's unclear which of these implications apply to our case. But it turns out that when testing if a state is product or not, meaning testing MPS with bond dimension equals 1, then a constant copy complexity is possible. So let me tell you about the algorithm that achieves this. I'll first tell you about a 2-copy version of the test, which doesn't depend on the distance delta. But then we'll see the performance can be easily boosted by repeating it a bunch of times. So this is a test first proposed by Mintert et al. And then rigorously analyzed by Harrow and Montanaro. And its basic building block is the swap test by Berman et al. So the swap test, as you might be familiar with it, is a 2-outcome projective measurement, even in terms of the swap operator. And we say the swap test accepts when the outcome corresponding to the identity plus swap over 2 is obtained. And it's not hard to show that the acceptance probability of the swap test, when given psi tensor phi as input, relates like this to the overlap between the two states. And this can be generalized to when the inputs are mixed states as well. And as a special case, the acceptance probability, when both states are the same, relates to trace of rho squared, which is the purity of the input state. So that was all about the swap test. Now let's see how we can use that to obtain an algorithm for testing product states. So as I said, the product tester involves only 2 copies of a many-body state, psi here. And it proceeds first by performing the swap test on all qubits and their copies. And the product test accepts if all of these swap tests accept. So what is the performance of this product test? If the input is in fact a product state, then the product test accepts with probability 1. And this is simply because each of the swap tests are acting on 2 copies of the same pure state. And based on what I just said, they all just pass. But perhaps surprisingly, it's shown by Harrow and Montanaro that the product test also manages to reject states that are far from product. So if the input state psi is delta far from being product, then this test rejects with probability delta squared. And in particular, if the input state has a constant distance to product states, this test uses 2 copies of the state and will reject with a constant probability. And intuitively, this is because if a many-body state psi is entangled, some of its subsystems should be mixed states. And we know the swap test may reject on these mixed states. Okay, so we can also repeat the product test on 1 over delta squared more pairs of states to prove this soundness from delta squared to at least 2/3, which is what we initially wanted in the property testing model. So a very interesting application of the product test is also given by Harrow and Montanaro, who show that the complexity classes QMAK and QMA2 are equivalent for k greater than or equal to 2. So what are these classes? QMA1 or QMA is the class of problems solvable by a quantum polynomial time verifier with the help of a prover who sends an entangled state psi as the witness. And QMAK generalizes this to k provers who send states psi1 to psi k as witnesses. And the crucial assumption here is that the k witness states that the provers send are not entangled to each other. So understanding the power of QMA2 and prior to the result of Harrow and Montanaro, QMAK has been a major open problem in quantum complexity theory. And the product test implies that these two classes are equivalent, or QMAK and QMA2 are equivalent. So let's see why.
In the background mute themselves? There's background noise. Jim, could you mute yourself?
Okay. Okay, so let's see why having the product test, we get this equivalence between QMAK and QMA2. And this is because, if the provers are all wise, as that's the assumption in these complexity classes, the verifier can, in principle, ask one of the provers to send the advice of k provers at once. But of course, the issue is that the prover can cheat by sending a k partite state, which is entangled across different subsystems. But if instead of one prover, the verifier asks two provers to send the k witness states, then the verifier can run the two-copy product test that I just described to see if each of the provers are in fact sending a product or an entangled k partite state. So two provers in this case just suffice for solving the problems that QMAK class can solve. And this result has very interesting applications in driving computational hardness for tensor optimization problems. You can see a list of almost 20 of these problems in the Harrow-Montanaro paper. So the original proof of the soundness of product test is rather elaborate, and it's been open if there is a simpler proof and also an improved analysis of this test, which brings me to our first result, which gives a simple and improved analysis of the product test, or equivalently testing matrix product states with bond dimension 1. So our main contribution here is a much simpler proof strategy. I'll just sketch it here, but the whole proof fits into one page. You can check it out in our paper. And in the proof, we use the Schmidt decomposition of the state psi across the first cut. And this decomposition gives us the Schmidt coefficients lambda, which form a sorted probability distribution. Now, let's assume that the state psi is far from being product. And we want to show that the product test will reject this state with high probability. So there are two possibilities here. One is that lambda 1 is small. And since these lambda coefficients are sorted in a non-increasing order, if lambda 1 is small, it means this distribution over lambdas is more or less uniform. And therefore, the first qubit is highly entangled with the remaining n-1 qubits. And in this case, the first subsystem is fairly mixed, and the first swap test that we perform with good probability detects this and will reject. So this is what we want. In the other possibility, lambda 1 is large, and say it's very close to 1. Then from the Schmidt decomposition, we see that the state psi is roughly equal to A1 tensor B1. So no entanglement exists between the first qubit and the rest of the n-1 qubits in this case. And therefore, the first swap test doesn't detect this and just accepts. But on the other hand, for the state psi to be far from product in this case, it has to be true that the state B1 is far from product states. And this simply means that the remaining n-1 swap tests most likely reject. And this implies the soundness of product test that I claimed earlier. So this rough idea can be made precise using an inductive proof. And by doing so, we get this upper bound on the acceptance probability of product test, which is in fact optimal for when the distance of psi is less than square root 1/2. And this is attained by this simple state psi on the slide. You can show this. So this settles the performance of product test in this regime of parameters. All right, so this was all about the case of testing MPS with bond dimension 1 for product testing. Now I'll tell you about our second result, which is testing matrix product states with any bond dimension. So the main ingredient we use is a property testing algorithm called the rank tester due to O'Donnell and Wright, which is an algorithm that tests whether a density matrix row has rank at most R, or if it's epsilon far from states with rank R. And as always, rank is just the number of non-zero eigenvalues of a row. So in their work, they managed to pin down the copy complexity of their test, which is R squared over epsilon. So for R equals 1, their test is the same as the swap test. But for the larger values of R, they use a generalization of the swap test, which is called the weak Schur sampling. And they show that their test achieves their test is optimal among all tests that have perfect completeness and order 1 soundness. So their M-copy test can also be efficiently performed with a quantum circuit, and the size of this quantum circuit would be polynomial in the number of copies m and logarithmic in the dimension of qubits. So this also implies that the MPS tester that I'll describe shortly can also be efficiently implemented. So what is our MPS tester? So it's a natural extension of the result to the states with n qubits. And the way it works is that it simultaneously performs the rank tester that I just told you about, first on the first qubit and its copies, then on the first 2 qubits and their copies, and so on. At the end, the MPS tester will reject if any of these rank testers reject or will accept otherwise. Okay, so what is the copy complexity of this test? We have both upper and lower bounds for this. So we show an upper bound of order n times bond dimension squared over delta squared, which doesn't have any dependency on the qubits dimension d. And this has a simple proof that I sketch here. So we want to argue that if the state is far from MPS with bond dimension R, then the rank tester with order n copies will detect this and reject. So to show this, we first show that if the state psi is delta far from MPS R, this implies that there is a cut such that the reduced state on one side of this cut is delta squared over n far from being rank R. And if we give sufficient number of copies to the rank tester that we had in the previous slides, which is performed on this cut, it can detect this, and with high probability will reject. Okay, so that's good, but we actually don't know where this cut is. And we are performing the rank tester on each of the n cuts in this state to detect this specific bad cut. So in the second step of the proof, we show that these rank testers that we simultaneously perform on all cuts mutually commute with each other. And therefore, the order that they're applied doesn't matter. And overall, they construct a valid projected measurement. So as a result, the location of this cut doesn't matter and will be detected by our measurements with high probability. So this order n upper bound is kind of very pessimistic, or the analysis is very pessimistic. And one question you might ask is if this analysis can be improved to potentially give a constant copy complexity, which was the case for product testing that I talked about earlier. And this turns out to be possible for a special state called the bunny state. And what is this state? So here you should think of the bunny's ears as 2 ones and the grass as zeros. So then the state is a superposition of the bunny hopping to the side. And what do we know about this state? We can show that it is an MPS with bond dimension 3. And with some more work, you can also show that it's constantly far from being MPS with bond dimension 2. So since this state is far from MPS 2, if we run the R equals 2 MPS tester, it should reject it with high probability. And the question is, how many copies of the bunny state do we need for this? So it turns out we can actually adapt an inductive proof strategy similar to what we have for our product testing, which I discussed earlier, to show that if the R equals 2 MPS tester is run on 3 copies of this state, it rejects with probability at least 1/6. Okay, that's cool. And for a while, this made us think the constant copy complexity should be possible more generally for other states as well. But now we know that this is not the case. So in our work, we show a lower bound of a square root n for the number of copies any MPS tester requires. And this applies not only to our particular MPS tester that I showed in the previous slide, but also to any other MPS tester algorithm. And the proof of the lower bound is somewhat subtle. I'll just show you a brief sketch here. Our hard example is the following state psi, which consists of a tensor product of 2 qubit states phi. And one nice thing about this state is that we can provably bound its distance to MPS. So remember that overlap with MPS R was just defined as shown on the slide. Now, if the 2 qubit state phi has an overlap of omega with MPS R, then the overlap of its n-half tensor products is just omega to the n-half. And this is something you might intuitively expect, but it's also not a completely trivial statement because we are measuring the overlap of psi with the states that may be entangled across all qubits, unlike psi itself, which is a tensor product. So you can check the proof of this statement in our paper. And in particular, this implies that if the overlap of the 2 qubit state phi with MPS R is like 1 minus 1 over n, then the overlap of the whole state psi is just a constant. Okay, now here's the trick that allows us to turn this state, which is constantly far from MPS R, into a hard instance for MPS testing. So suppose we take this bipartite state phi and apply 2 local unitaries on its qubits. So this clearly doesn't change its distance to MPS R because the rank of the reduced state doesn't change. And any MPS tester should have the same performance on m copies of this state phi, no matter what local unitaries we've applied. And this holds even if we consider an ensemble of random unitaries applied to phi. And the same argument applies even if instead of phi we consider its tensor products. So this gives us random rotations of the state psi, which is across n qubits now. And as I just described in step 1 of the proof, we know that this state is constantly far from MPS R. So now it can be shown that there is a bipartite state gamma, which is in MPS R, such that unless the number of copies m is at least the square root of n, the random rotations of this gamma is close in trace distance to the random rotations of phi. And this means that the MPS tester won't be able to distinguish these random ensembles from each other. So in summary, we have a state psi which has a constant distance from MPS R, but when it's randomly rotated, and we are only given a fewer than a square root n copies of it, it's close to some random ensemble of states in MPS R, and therefore MPS testers failed to detect this. Okay, so in summary, I told you about testing entanglement, and I basically covered 3 results. One is a simpler and improved analysis of the product test, which corresponds to testing MPS with bond dimension 1. The other is an upper bound of order n on testing MPS with any bond dimension. And finally, a lower bound of a square root n for testing matrix product states, again, with any bond dimension. And here is a list of open questions left by our work. The first question is whether we can pin down the copy complexity of MPS testing. So is our order n upper bound tight, or our square root n lower bound, or is there something else going on? Another question is going beyond MPS. We can think about testing more general entangled states, such as various forms of tensor networks or low-depth quantum circuits. And also, this talk only covers testing entanglement in pure states. And testing entanglement in mixed states is a very fascinating problem of its own, with many open questions, such as simply testing if a bipartite state is separable or not. And I think with that, I've covered everything I wanted to share with you, and I thank you for your attention.
Is there a question from the audience?
So I just want to quickly, so your upper and lower bound, there is a gap, right? For the upper bound, you require roughly n copy of the state, and for the lower bound, it's square root of n. Do you think which one is more likely to be optimal, or anything in between?
Yeah, that's a good question. I don't have a good answer. Like in the course of this project, we we change our opinion a lot. As I mentioned, we had this like order n upper bound first. Then we discovered these like bunny states that they just need a constant copy complexity. And then we realized this is not, universal. There is a square root n lower bound, but we haven't been able to improve our square root n lower bound. And it makes me think, if I wanna guess, that there is an improved analysis of our MPS testing that is similar to the analysis of product testing, which makes it better than order n. But I don't know if it would achieve square root n or not. Like, I'd be very surprised if order n was the right bound, but it also might be. I don't have a good intuition for it.
You use the rank tester as your technical tool, right? Could you remind me again why looking at the rank is a good way for this problem?
Right. So let me find the slide. So there are two definitions of MPS. You should probably see it on the slide right now. One is that you just write the coefficients, the amplitudes of the state in terms of R by R matrices. But equivalently, you can think about MPS as set of states that if you look at the reduced density matrices across any cut, the rank of the reduced density matrix is less than R. So then one natural way to test MPS is to just check all the cuts and see if the rank is less than R or not.
I see. Okay, thanks.
You're welcome.
So any
Hey.
Okay, I have a question. In some slides you mentioned you use the AB to verify something. Are you going to be the magic product that can be by part-time or for which purpose? And probably I again.
Sorry, I didn't hear the question very well. Can you repeat it?
I mean, in some slides you use the technique cut. You mentioned you can find the cut AB to find the part-time product for which purpose. Cut AB in something like.
Yeah, I don't have a. Yeah, I don't hear very well. Sorry, can you repeat it again? The voice is disconnecting.
Can you go back to the slide with the cut AB?
With the path AB?
Cut. You use the technique to cut AB into bipartite.
Right. Let me try to find.
Probably in the middle.
You mean here?
Yeah. So
Okay.
you use cut AB means you are going to find if the mesh product can be bipartite or for which purpose. Why do you need this cut AB?
Right. So what do we want to do? We want to show that if the state is far from being MPS with bond dimension R, then the rank testers that we perform, so we are performing multiple rank testers as shown in this slide. So what we want to show is that one of these rank testers will reject. So when do they reject? When they detect a rank more than what we ask them, right? If the state is far from MPS, there are basically two extreme ways to increase the rank of one cut for it to be far. One is that you put all the weight on one cut, and then that makes it be far from MPS. The other is that you share the weight across all n cuts, and then again that makes it far from MPS. In the first case, if we put all of our weight on one cut, one of these rank testers will easily detect, right? In the other case, when we are like kind of uniformly distributing the weight across all cuts, these rank testers will have a harder time unless we give them sufficient number of copies. So what this theorem is showing here is that if you are far from delta, far from being an MPS, there always is a cut that you're at least 1/n far from being rank R. So this is like a very pessimistic analysis, right? As I said, you can be in the case that you have a much higher weight on one of the cuts. You don't need to be like 1/n far. So what this shows is that in this like pessimistic way of thinking, order n copies suffices for testing MPS. I don't know if that answered your question there.
Yeah. So the cut is between different copies. So you are trying to say there are some certain cut that can give you the good way to see if the length can be limited.
Right. So the cut is just so by cut I just mean a bipartition of the state into two sets. And this shaded area here is just saying we have this rank tester that is being performed on qubit 1 through something which we called A, and their copies. Mm-hmm. And we are saying from the perspective of this rank tester, the state is 1/r far from being rank R. So say delta is constant. By 1/n, I just mean like delta squared over n, but let's just say 1/n. And therefore, if this rank tester has enough copies, which is order n, given by this amount here, then it will likely reject.
I see. Okay. Okay, thank you. Sorry, another question is about when you find the product state test, if the state is placed, does this give you some good way to reconstruct the matrix? I'm thinking about the tomography. If you are trying to reconstruct a matrix, either mixed states, or is this a good way to find application in the tomography if you want to recover some density matrix, if you can find the closest product state?
Right, that's also a good question. So there has been previous work on learning these A matrices in the MPS, these like matrices that define the state. And one strategy for testing MPS is that you first run that tomography algorithm. It's due to, let's see, do I have the reference for that in the slide? I mean, I can find it later. Right, it's due to Kramer, Pliny et al. So if you have this efficient tomography, you can run it and then use that to see if your state was bond dimension MPS with bond dimension R or not. And I don't know if we know the optimal tomography algorithm for MPS, but usually it's the case that the optimal algorithm has a copy complexity proportional to the number of unknown parameters that you want to learn. So in this case, for MPS, we have n times d times r squared parameters. So let's say the copy complexity of tomography is that. And then you just use your algorithm, you learn, and you then test if the bond dimension was R or not. This would still be worse than that order n upper bound that I showed in the other slides. And the reason is that there is a dependency on D, the local dimension here, which we don't have when we use that strategy of rank testing across all cuts. So even the optimal tomography algorithm is still an order D off from our upper bound.
Mm-hmm. I see. Okay, thank you very much.
You're welcome.
That's interesting. Yeah.
So is there any further questions? Okay, if not, let's thank Mehdi again for today's nice talk.
Thank you.
Thank you.
You're welcome.
Bye-bye.
Bye.